All right, let's go ahead and get started. Really excited to kick off our InTERFEWS program today. Thank you everyone for coming. This has been a long effort between the project team to get this program going, and we're really excited about it. Thankful for you students showing up also. I think since we have a small group, let's just go ahead and do a round of introductions. I'm not sure I need to introduce myself, but Sybil Sharvelle. I am the PI of this InTERFEWS program, and I am in the Department of Civil and Environmental Engineering, and you're going to hear a lot about my research today. Sarah, why don't you introduce yourself too?
I'm Sarah. I'm the Assistant Director for the One Water Solutions Institute and have been helping with the coordination of this program.
My name is Rich Conant, and I'm a professor in physics.
Ken Reardon, I'm a professor in chemical and biology.
Hello everyone, my name is Sybil and I'm a PhD candidate in the Civil Engineering program. I'm working with the topic of research is public works.
I'm Max Rabbe, I'm working in outside and my research focuses on database analysis, especially the conserve plot.
Show also civil environmental engineering. I'm on paper starting my PhD this semester, but also finishing my master's research in water infiltration industry.
My name is Luke Fletcher, and been one of Civil students for a number of years. Now a PhD student in systems engineering. I've been working in anaerobic digestion and now I'm working on a photobioreactor for anaerobic digestion.
My name is Samantha Jeffrey. I work with Dr. Sharvelle, a PhD candidate. I work on pathogen characterizations on water and evaluation.
Civil engineering.
And Stephanie, do you want to introduce yourself quickly?
Sure. I'm Stephanie Malin. I'm an associate professor in the sociology department and with the Colorado School of Public Health.
All right,
and
thank you.
Yeah, on the project.
Yes. All right, well, thank you everyone. And like I said, really excited to be here today and kicking off this program. The purpose of this seminar series is really for, first and foremost, the project team to get familiar with each other's research and try to find the interdisciplinary collaborations that we are seeking, and for students to start to gain from some of the resources that we're going to be providing through this program. And so we wanted to start to engage students in this process, and they'll be all, even if you are not at a point in your graduate program that you can apply for this program, there'll be many resources offered through this program that you can take advantage of throughout your degree program, and we want to get you connected to all those kinds of opportunities. So that is what we're doing, and so today I will be talking about the role of urban water efficiency and resource recovery in food energy systems. I'm going to start with a brief overview of the program and provide opportunity for project team members to describe more, or for students to ask additional questions if you happen to have those. And then I'll start talking about the research. And a lot of this presentation is a lot more on informing potential research questions that I'm hoping that InTERFEWS and future trainees in our group can really work together to make discoveries on, and some presentation of my current research as well. Okay, so the InTERFEWS program is a training program for graduate students. It is focused for PhD students, and so the students in the room here today are PhD students, so should be relevant. The mission that we have is to prepare this diverse cohort of graduate students with transdisciplinary skills and systems level thinking necessary to make meaningful contributions to the complex and changing interactions in food, energy, water systems under water scarcity. So our location here in the Front Range provides a really unique opportunity for us to be able to study these problems, being that we are a semi-arid region and water scarcity drives a lot of pressures between our resource allocation between food, water, and energy. And so we have that additional pressure here on our water systems that creates that kind of scarcity and provides some really interesting topics to study in this environment. And we also at CSU have a longstanding tradition of work in water, food systems, agricultural production, and energy systems. So really nice opportunity, I think, for us. So the program for InTERFEWS includes curriculum, which is coursework, research activities, which are part of any PhD program, some professional skill development that you can engage in, as well as apprenticeships. So those trainees that are awarded fellowships will need to participate in all of these components of the program, but there will be a lot of professional development activities really focused on developing 21st century job skills, and not just skills for academics, but also for those wanting to work in industry jobs when they, or government agency jobs when they complete their degrees. So those will be some really nice opportunities for some of these students, I think, to tap into. And then there'll be these apprenticeships that students, trainees will need to engage in, which is a couple of months working maybe with a nonprofit organization or a city doing something that may be related to your research, but that really equips you with new skills that your regular research may not have done. Okay, so just a little bit about the application. It's for PhD students entering first or second semester. That is, we really want to develop a cohort of students and multiple cohorts of students that we want early PhD students, but I'm really hoping that some of you others can take advantage of this. The stipend is $34,000 per year, and then also tuition coverage. Unfortunately, that only is applicable for U.S. citizens, but I am working to get tuition coverage for non-U.S. citizens. So that's kind of in the works currently. By the way, feel free to ask questions. This is a small, intimate group for a reason. We want to encourage discussion. So if any questions arise, feel free to interrupt me at any point. Okay, so applications due by April 5th for best consideration. And as an applicant, the applicants will select research projects. So there's been a lot of solicitations out for these research projects. There's a lot of faculty outside of our group of 10 that have expressed interest in working in and contributing and mentoring students, and they're already working to submit project proposals. And the research really needs to integrate systems analysis tools with social and economic analyses, and these transdisciplinary projects that include systems level thinking. So mentors are proposing projects right now that include these components, and we're vetting those to ensure that those components are included, because it's really critical to the success of this program that the research includes those particular components. Okay, so that's it on the program. Anyone have questions, or would any of our project team like to add anything in addition to what I said? Yeah.
So you're still accepting applications for projects. Is there a cutoff date? Are you expecting those projects to be finalized before April 5th?
Well, yeah. So what happens? And I forgot to explain this part. So thank you for that question, because how that will work is that the students are going to be selecting projects that they're most interested in, a couple of projects potentially. So if we're going to be making, if the students are submitting their applications by April 5th, then the projects that they would want to be working on kind of need to be posted. It's mentors' responsibility, though, to get those project proposals submitted, and then we post them onto our website so students can see. And we've already been adding additional ones in the last couple of weeks here since we made the call for those. Jumana.
Other courses.
Yeah, thank you for that question too. I meant to talk about that. So that's another resource that I think is great for students to take advantage of. Next semester, we'll have a course that's kind of a survey course on food, energy, water systems. Dr. Kona is co-teaching that with me, in addition to Stephanie Mallon, who's joining on the phone, and Chris Gomans in economics. So that class will provide some of the systems level thinking, an understanding of each food, energy, water systems. The learning will really be through case studies and a lot of the thinking that we're expecting students to have will be introduced into that class, and that is open to students across campus as long as we can maintain a diversity of students across disciplines. So that'll be key, but definitely want students outside of the InTERFEWS trainees to be taking and benefiting from those courses. And there's another one that's tools, analysis tools for food, energy, water systems that MASDAC will help teach, that it gets more into some of the risk analysis and things of that sort. Other questions? All right. Then we can go ahead and get into the research area of resource recovery and urban water efficiency and connections that happen there between food, energy, water systems. So I'm going to be talking a lot about urban water systems today. So I'm going to start with an overview of the urban water system and then get into some components and where resource recovery can happen and how that gets connected with food, energy, and water. So we have our water supply, and the first part that happens is water is treated and distributed out to an urban area to meet end uses. And this shows a very conventional water system. We're rapidly, I think, rethinking this system, and a lot of work is happening with our urban water innovation to assess those kinds of things. But I'm going to start with the conventional system. So people use the water in their homes, or there's industrial uses, commercial uses. Wastewater is generated, we collect that, and we treat it to meet a quality appropriate for discharge in a receiving water body. Okay, so that's been our traditional approach. We also have stormwater, and that will come up today as part of an alternate water source. But we're first going to kind of focus in on this wastewater treatment part. And we have traditionally spent a lot of money and energy to remove carbon and nutrients from our wastewater to make it of a quality so that it can maintain healthy ecosystems in our receiving water bodies. And that is rapidly changing, where we're starting to think about wastewater treatment facilities more as resource recovery systems instead of places where we just remove those nutrients and carbon. So we end up putting a lot of money and energy into getting a quality of water that's appropriate for this discharge. But like I said, we're rethinking that, and we want to take and extract resources as much as possible from wastewater facilities and really view them as resource recovery systems. So like I said, our municipal wastewater is high in carbon, nitrogen, and phosphorus. That's most of what we're trying to remove before we discharge it. But we can take, for example, our nutrients, the nitrogen and phosphorus. There's nutrient extraction processes that can get us fertilizers that are like crystallized fertilizers or liquid fertilizers that can be used then for food production systems. We can also recover our nutrients in the biosolids, where we can uptake phosphorus and nitrogen, and there's going to be carbon as well in those biosolids. So there's kind of two ways to think about those nutrient collections. Those kind of crystallized or liquid products are ones that are really more attractive, I think, for agricultural producers. But agricultural producers by Denver Metro Wastewater Facility will tell you that they highly value the biosolids that are produced there and that they help a lot with crop production. So they're all attractive products where we can extract nutrients. Okay, so we can also take the carbon in the wastewater and convert that into energy. Is there a way to get that down? That's okay. Okay, so we can use anaerobic digestion and make methane from the carbon. We can supply that back into a natural gas pipeline. We can use it for vehicle fuels. We could use it for a generator to make electricity. So there's a lot of options. Here you see a city fleet, a fleet of city vehicles where they're taking biogas or methane from an anaerobic digester and using it to fuel the city vehicles. And that's something that a lot of cities are looking at right now. And we can, of course, also recover the water. So now we're looking at recovering almost all of the inputs from the wastewater facility and turning those into valuable resources. And we can think about water recycling systems for food production, for toilet flushing, or to drink for creating potable water. And we have technologies that can purify water really to any quality that we desire. It's just a matter of fitting that treatment to the right end use. So we can see there's all sorts of food, energy, and water connections that happen here, with the potential for increasing nutrients for agriculture production and making energy and reusing water and decreasing the demands for maybe freshwater sources. These are all technologies that wastewater facilities could be using, and some are piecemeal using in different areas, but adoption is not very high. I haven't seen a facility yet that does all of this to a high extent. And I think that a lot of the reason that there's some barriers to adoption is that we don't quite understand all of these food, energy, water connections yet. So the utility manager is thinking about their end goal is to discharge water into a receiving water body. They have not converted into really thinking of themselves as a resource extraction area. So there's that kind of change in thinking, but there's also the driver for a wastewater or utility manager to adopt all of these technologies may not be there. And we really need to understand those food, energy, and water systems level potential benefits of these practices that could maybe serve as additional drivers to increase adoption of these different practices. Any questions? Oh, East Bay mud. So this is a good example. So I just showed we can extract carbon from wastewater. East Bay Municipal Utility District in California was the first facility to do codigestion, where they had additional capacity in their anaerobic digesters, and so they collect food from the municipal waste. So they get food waste and also process that with the carbon in the wastewater that comes to their facility. So that's a codigestion project, and been really successful, really boosted up their energy production. They produce enough energy on site to completely meet the demands for their facility, and a lot of times provide additional demand to the city. So a lot of facilities popping up that are starting to look at, because they may be over-designed or oversized their anaerobic digesters, and looking for ways to make more methane through food waste collection. And it works really nice for cities that are trying to achieve landfill waste diversion as well. Okay, so I've been talking about this process already of anaerobic digestion, but I kind of just said we're taking the carbon, we're turning it into methane. That is what happens. It's a biological process, but this process can be used for a lot. We talked about it with wastewater and maybe the codigestion with food waste. Yard waste can be processed in these systems, animal manure. There's all sorts of high organic content waste that can be captured and converted into energy through these kind of systems. And again, we get a lot of connections with food production systems when we think about this, because our food production facilities produce a lot of waste. Sometimes crop residue can serve as a source in these. So there's all sorts of different ways, and we can still compost a solid end product, end up with nutrient recovery from these systems as well. Yeah.
So maybe you're going to get to this, but I think it's worth mentioning that the Department of Energy has been funding research to do essentially an advanced version of this and produce not methane, but things, chemicals, and potential fuel precursors that are higher value, higher fuel.
Yeah, so a big part of what's going on right now with anaerobic digestion is that currently methane doesn't hold a lot of financial value. I talked about some of these systems level benefits that are likely, but there's not a lot of financial benefit from capturing and using methane given the current market. So a lot of people are looking into, I have this first step here, organics to acids. So we can actually stop the process there and make organic acids that can be used to make plastics and And other fuels, what are some of the other things that those are used for, Ken?
Yeah, there are plastics precursors, but it can make higher order fuels. Like
Higher value fuels is the big
thing. Turn butyric acid into, for example.
Right. Mm-hmm.
That's a better fuel. It can even go into jet fuel.
Right. So again, just a lot of these connections happening there. This is a technology that we've been working on in my research group. Luke has been here for decades. Giving him a hard time. But he did leave for a little while, and then he came back into the systems engineering. This system was first conceptualized when Luke started his master's degree with me, and we were trying to overcome this issue of feedlot waste anaerobic digestion. Feedlot waste is generated in very high quantities. It's really a nuisance right now, especially in our region, including Colorado up to Wyoming and into Texas. But it's really high solids content. It's got a lot of rocks and sand and things. So this is a technology that we've been working on to overcome that, some of those challenges. And it basically, we circulate water through the system, generate a leachate, and then anaerobically process that leachate and still compost the solid material. And we're working on some research right now to capture nitrogen from the liquid stream, which helps the process run more efficiently, but also provides potentially additional revenue stream, or again, helps balance some of these resource allocation between our food, energy, and water systems. Okay, so resource recovery in these food, energy, water connections, I already mentioned the systems level impacts are not necessarily well understood. We kind of know they're there, but they're not very well understood. And are there systems level connections that may open up new drivers for adoption of these technologies and practices? Are there considerations from a systems level perspective that may make some of these practices not look as good? Those are some of the things I hope to be exploring with the group during this project. Okay, so now we're going to move more into, we've talked about this wastewater part and some of the municipal and other solid waste that contain organic matter. We're going to move more into the water supply side now and talk about energy and water connections that can happen there. Okay, so this shows City of Fort Collins energy expenditures. And this is for the utility. And this is pretty common throughout the country. Actually, a lot of cities spend more energy than the City of Fort Collins does for water supply. What do we benefit from? I'm going to look at the students. What do we benefit from here in Fort Collins that helps with our energy for water delivery? Gravity and lack of pumping. So for a lot of cities, and particularly in California, where water is sometimes transported very high distances, there's a lot of energy consumption that happens with water supply. For our city, most of the energy consumption happens with wastewater, but we have still 36% of the energy profile is related to water supply and wastewater treatment. So there's some nice opportunities to conserve energy in water supply and wastewater treatment and really achieve some more systems level benefits. Now, I don't like this figure, but it's not data that is mine. It's an older study, 2002, but I do think there's an interesting point I want to make from this figure, which is, I think, probably even hard to see on this, but what this shows, so this goes through a projection of energy for water supply up to 2050 for the United States, and looks at your baseline projection based on if we keep on doing what we're doing, then that's what the baseline projection does. It looks at increased per capita water use and then increased electricity consumption for supply of water, so either for treatment or for supply, and it looks at decrease. Take-home message here is reducing per capita water use is far more effective. That's its bottom line here. That's the lowest energy. It's far more effective than trying to get more energy efficient treatment systems. So whatever we can do on the supply side of water to achieve some energy efficiency is really going to have a lot of benefit. So water demand reduction is most effective. Okay, so what are the strategies that we use for that? So there's water efficiency, like water conservation, where we use indoor fixtures, efficient irrigation systems, xeriscape, so changing our landscape into xeriscape systems. And we can use alternate water sources. We can use wastewater or gray water, stormwater, roof runoff, and that decreases the demand for municipally supplied potable water. Okay, so there's all of these different source water end use combinations. So we have water from toilets, from laundry machines, from showers, from storm events that could either be collected off of a roof or from parking lot surfaces and roads and really large scale stormwater collection systems. We have various potential sources of water that can be used, and then all of these different end uses as well. So we can use them for toilet flushing, irrigation. Those have been the most common and first end uses for water recycling systems. And we're now looking toward using those for using these sources to make potable water as well. And like I said, we have the technology to purify water to whatever quality that we want that's appropriate for the end use. But there's this concept of fit for purpose water, which is appropriate treatment of water based on the source water end use combination. I like to think about it as right treatment for right use. Okay, so it's really taking the source water into consideration and understanding how much treatment is needed to ensure safe water is delivered for the particular end use application. So there's different levels of treatment that are needed depending on that source water and end use combination. So we're moving really toward a paradigm of understanding what those levels of treatment are and being able to implement them. And that means, again, we can potentially save energy and money if we're not treating all of our water to potable quality, and we can treat it a little bit less, maybe to flush it in a toilet or use for irrigation, then we get some financial and energy benefits associated with that. Even further, when we start talking about building scale systems for collection of gray water or wastewater, there's some other things we can do to even further reduce energy. This is the Solaire building. It's in Battery Park in New York City. Any of you guys go to New York for the projects at Mastic? No, none of you guys. Okay. So maybe you've been to New York and seen Battery Park. It's a nice area. They've got this huge building here. It's got an on-site wastewater treatment system that looks like this, where they collect the wastewater, treat it on-site, and use it for toilet flushing in that building. They've achieved a lot of water demand reduction through this project, but probably more interesting is that recently they've implemented a heat recovery system into the process, since the water is collected right on site. If you think about most of your wastewater, it's hot. It's from showers, it's from dishwashers, it's from laundry machines that we usually use hot water for. So there's a lot of heat to be captured on site, and there's much more heat on site than what we get from municipal scale wastewater. So they've added in to this building the water reuse with heat recovery. They actually save both money and it's energy positive. So meaning that, so they're actually saving energy from what they would be otherwise. So they're using the heat to heat building potable water. So they're not taking they take the heat from the wastewater and use that through heat pumps to heat water supply and water heaters. And they save a lot of energy in their building by doing that. So they recover more energy than what they use for treatment and actually have an energy positive system. So I think that that's a really nice example of how we can be rethinking these systems for energy considerations. So our research group lately, and these are results that Michael Neal has been working on, a lot of you know him, Our research group recently has been working on looking at costs associated with all of these different water efficiency and demand reduction strategies. Okay, so this is a multi-objective analysis strategy where we're looking at, on the x-axis, our annual demand reduction, and then the cost to implement these different technologies. Okay, so these points all represent multiple combinations of all the strategies that you just saw. So the water efficiency ones like xeriscaping, combined with the use of alternate water sources. So we had hundreds and hundreds of different scenarios. And then we identified kind of this freedom front where we have non-dominated solutions for looking at per capita cost and demand reduction. This is just an example for Denver. So that just kind of shows the methodology. This graph, I think, is then really interesting to look at. And I'm just going to take a minute to orient you. So all of these are all abbreviations. It's hard to write these all out. So they're all on this right-hand side. So, for example, GW is gray water, WW is wastewater. Then we have the different end uses and then the conservation strategies. So this graphs out the demand reduction in 3 different cities. We looked at Denver, Miami, and Tucson. And we can see that some of the strategies like efficient irrigation systems, those come up really well for demand reduction everywhere. But some of the other strategies, SW for irrigation, for example, is most effective in Miami, where they have more stormwater generated there. We see also some things like xeriscape. Yeah, xeriscape is not as effective. Well, actually, Denver looks really good for xeriscape, and part of the reason for that is that already in Miami, people use more climate-appropriate landscape, and also in Tucson. So there's not as much benefit for them to gain there, whereas Denver has a lot of green yards still. Okay, so this allows us to really look at identifying the strategies that are most cost-effective, but we still are missing that piece about energy. But so this now shows the frequency. This is kind of another version of that same graph that has all these same options here. And for each of these, we're looking at, so your darkest part of each of these bars shows the high cost, the frequency of high cost, frequency that these came up in what we call high cost, which is greater than $40 million per capita, $40 per capita, sorry. I think that's on I don't know what the time of that is actually, but regardless, those are the highest cost solutions. So you can kind of see how these distribute amongst high, medium, and low, and the lightest part is low. So indoor conservation, for example, shows up mostly light. That's a really cost-effective strategy. It doesn't achieve as much demand reduction as some of the other strategies, but it comes at a really low cost. So we can really look at these trade-offs between cost and demand reduction. But like I said, we're missing still that energy piece. So it would be really easy now that we know the kind of costs and treatment systems that are involved in all of these different strategies to now take that and look at what is the energy requirement for each of those, or energy savings that each of those can achieve, and what is the carbon impact of all of those different strategies. So I think there's a lot of ways that we can build to really look at these things through the lens of energy now. Decisions, we started with cost because decisions at utilities are often made based on cost, but I think there's a lot of new interesting things to explore related to energy. Okay, so I don't want to spend any questions on anything before I go on to this. So we have kind of outlined this driver pressure state impact response framework to be a guiding theme through all of our research, education, and training efforts. So if we start to think about all of these systems level interactions between food, energy, water systems, and how that interacts with resource recovery systems, it gets complicated very quickly. So we've decided to use this framework, which looks at these drivers, pressure, state, impact, and response, to try to better understand and frame the systems level interactions with these options. So we look at drivers, things like urbanization, population growth, migration, climate change. These are the things that kind of drive us to start to adopt maybe technological solutions or social or policy responses related to these systems. And what's kind of important, I think, with this framework and diagram is that it's not linear. Okay, this continues. There's a cyclical process here where we have these drivers. Those can cause maybe a response, like we've just talked about resource recovery systems, right? And water reuse. So that could be a response to overcome these and have maybe some good impacts related to some of these drivers that are creating problems. And so then we have to understand again how those, so if we have a response, then we have to kind of think about how that now impacts a new set of drivers, states, and impacts. And I think another important consideration is maybe we don't yet understand all these drivers. I've kind of referenced that a couple times with respect to some of the resource recovery systems that we haven't really totally understood the systems level interactions, and we may find new drivers that we can put up here with respect to those technologies. So just talking about the drivers for water recycling, these numbers aren't too important. These are the EPA regions, which is just kind of a nice way to separate the United States into different regions, but our drivers for water recycling are really different in different parts of the United States. We have a lot in the western United States, and there's water recycling projects on the eastern United States, and especially stormwater harvesting projects in the east, and I'll talk about that. And in the western United States, we think a lot about implementing these practices to achieve water supply reliability and resilience. And a huge driver is sustainability. So communities want to adopt more green practices. I showed you that Solaire building. It's been shown that buildings that adopt these kind of green practices have higher value real estate. So there's a lot of initiative and push towards sustainability. So that's kind of what's driving some of these projects now here in the western United States, and especially here with, like I talked about, our competing demands for water, for energy and food systems and urban growth. We really think about how to use water efficiently. In the East, water supply reliability is last on my list here, because there's some, in the Southeast, there's some intermittent drought periods that they have to deal with, and having alternate supplies can help increase reliability during those times. But a big part of their drivers are combined sewer overflow reductions and algal blooms and nutrient load reductions. So they think about reusing wastewater so they don't have to discharge it into receiving water bodies and impact those algal blooms. Okay, but we already talked about some of this water recycling and how there's energy efficiency to be achieved there, but is that potentially a driver? I don't know. I would be interested to know. We saw in the Solaire building, we actually created an energy positive system. So maybe there's benefits there. Okay, so these are just some of the research questions. I think I've already talked about that. So we have, what are the impacts of urban water efficiency on food and energy production systems? Particularly, MASDAC has done a lot of research through Water Sustainability Climate Center on how some of these urban water use strategies can impact our water availability for food production systems. I think there's a lot of interesting work that's been done there, and probably a lot of new questions we can be answering with respect to that too. And what are some of the social environmental justice impacts of these water management strategies and resource recovery systems that we can begin to understand? So these are all research questions that I'm hoping that we can address through this team and through this program. And last concluding note here, transdisciplinary research is absolutely essential to solve these problems and answer these questions. And we've got to have research that's stakeholder engaged and that works across the disciplines of natural sciences, engineering, and social and political sciences and economics. So we've really got to put our heads together to solve these problems, and I'm really looking forward to working with this project team to address some of these questions and potential existing students here and new trainees to wrap our heads around these things. So that is where I'll conclude. Questions, comments, thoughts? Yeah.
How many students do you think will be hired this year? Or
yeah, I know we're going to have a lot of applicants. I'm getting that vibe. And we had originally planned for funding 4 students this year. And we would have another 4 that would be part of the cohort that are unfunded. So that's a total of 8. We could increase that. My thinking, as we'll talk about this more with the project team as we move forward, is that our first cohort, it might be nice to have a little bit smaller because there's going to be some lessons learned in that first year, and that we start to expand it more in the second and third years. And I think we'll also really be able to beef up recruitment activities in the next year to increase the potential of that next cohort as well.
So I guess I have 2 questions.
Sure.
But start the first one maybe because we'll kind of group here. But what are the main opportunities from each person's kind of area where they are seeing systems thinking being important to these kind of overall questions, and overall outcomes, I guess, in the future? And I know that kind of bringing together people from different backgrounds, what is kind of the difference in perspective or focus that on your team?
Yeah, I think that I answered that a little bit in my presentation, but I'd love to hear from other project team members.
Yes, I thought that was the point of this first round of presentation.
Yeah, so Ken started when he came in. He asked if I'm going to explain what the point is of these presentations. That's what I see as the purpose of these presentations and what I'd like project team members focusing on as they develop their seminar talks, is to really think about how does their existing set of research fit in with systems analysis and transdisciplinary research. So that is something I think that each of us will be covering as we go through our seminars. I don't know if any of you have anything to add at the moment that would be a brief synopsis. Okay. Second question.
Yeah, so I guess kind of now come from the project in general, like what are you hoping to equip kind of the next round of academics? You mentioned professionals as well, but to go out and practice these?
Yeah, so that's the first goal. So let's just go back to our mission. The first goal is that these cohorts of students that go through this program are really prepared with job skills across different types of jobs that they may go into, and can really think about these systems level problems. And like a sociologist, for example, maybe would gain some understanding of some of the technical solutions. Vice versa, those of us in engineering and more technical fields can gain some understanding of how to incorporate social considerations and policy and social environmental justice issues, with Stephanie Malin works on, into our thinking as we address these problems. So that's kind of the short-term goal, is that this cohort of students graduates that is equipped to address these problems. But over the long term, we want these classes to sustain at CSU. We want CSU to have a name in food, energy, water systems, and for us to be thought of as a place to really prepare students over the long term for careers that address those kinds of issues. And I think the systems and transdisciplinary skills are probably even more important than just the understanding of food, energy, water systems. So really creating programs here at CSU that enable and foster that kind of education moving forward.
Maybe as a follow-up to that as well, is this a marketable concept to other, like, for those of us looking at academics, marketable outside CSU, I guess, or outside of the understanding here?
I will say that right now, with the problems that we are being faced with in water and energy and food, we have to get out of our disciplinary thinking and work across disciplines. And that's where the larger projects are in research, and I think in industry as well, when we can make those connections. So I would like to think that having a program that equips people with these kind of skills would make them attractive in the job market, and that's our goal. Anyone want to add anything to that?
I just said I completely agree. I mean, one of the things that, for example, the National Science Foundation is not requiring, but strongly encouraging a lot of now, but the phrase that you basically the societal implications of the research conversion.
Yeah.
And so you as funding agency is really, really important for academics. But this idea of thinking research beyond the already been going on.
Success of the PhD students after graduation, whether it goes to academia or any discipline or any industry, it's up to you. But as individuals, we have a portfolio of knowledge base and skill sets that allows to get have to build a career. The concept here is that our traditional approaches to education don't lend themselves very well to solve big global grand challenges. We need to improve our understanding as engineers how social policy and economic factors work. As economists and social scientists, we need to understand how to develop and design technological solutions. So now the most important factors that you hear in funding agencies or even in projects that are coming together in industry is we need to think about systems, not components, subcomponents. So in 20th century, we did a great job learning how to optimize delivery of services, break systems to subcomponents and optimize them. Now we're learning that doesn't lend itself very well for health of our community. We need to think bigger than just one individual component. Think within systems that encompasses, they call it social technical or technological, and people call it different terms, social, ecological, environmental, technological domains. I think success of any individual depends on what you know, and our hope is to provide an opportunity that our students learn skill sets that allow them and enable them to work with others in transdisciplinary. Transdisciplinary means not only across disciplines, but also with stakeholders, learn their problems, and so bringing them on board. So I think that's the core of this program, is to provide the opportunity to learn those skills, and how to apply them to solve some real world problems.
And it's hard. It really is. I mean, when you get a group of water engineers in a room and try to get them, even I would say on our UN project, when we have got people working on water, wastewater, and stormwater, even though those of us in research talk all the time about integrating systems, it's hard to actually do it because you have to get people out of their comfort zone of what their core knowledge base is and get them to think about the other components. And we tend to not be comfortable with that. And that if I would really like for this program to provide trainees and those of us that are involved with the confidence to get out of those comfort zones.
Sybil, can I add something as well?
Please.
Okay, I'm sorry to be talking from the computer, and I'm only hearing parts of what people are saying, so forgive any redundancy. But I want to mention, I think in agency settings, this knowledge could be incredibly valuable. I've worked a little bit in natural resource management, collaborative kind of settings, and having knowledge across systems will be invaluable, especially for somebody coming from the social science. Well, I shouldn't say especially for, but someone coming from the social sciences, for example. Having that more systems level of thinking in these more technical fields, like you said, I think can only help in those real world situations, right? Where we're trying to talk to a bunch of different stakeholders about the issues they're having across all of these different sectors, right? So I think it'll be increasingly marketable, and it is already.